Let us discuss Drude theory of metals. Before going into the detail of this theory, we must go through some historical facts, and among them, I want to mention that George Ohm, a German physicist, published a paper in which he explained that current I through a resistance R is directly proportional to voltage, or you can say voltage applied across this resistance, and he found that the current is equal to voltage divided by this resistance, and this R is constant for a particular wire or metal wire through which current is established. This is one fact, and this was given by George Ohm in 1827. This is one fact. Second is the discovery of electron was made by J.J. Thomson in 1897, and from here we know that the Ohm's law, that is which is linked with the current, was pronounced much before than the discovery of electron. That means it was known that when voltage is applied across a metal wire, then current is established, but it was not clear that what is that which makes this current inside the wire. So it was always the point of interest or findings that how current is established in the wire. So when J.J. Thomson discovered electron, then this interest of finding the reason of the electric current in the metal wire was on increase. One more fact we must know, that is, according to kinetic theory, kinetic molecular theory, all the molecules in a gas sample are always in random motion in all possible directions, and this motion depends upon the temperature of the sample. These are the few facts from which this Drude theory was influenced, and Paul Carl Ludwig Drude, a German physicist, he pronounced a theory to explain the conductivity of metals and to explain this Ohm's law and to explain why thermal conductivity and electrical conductivity depends on the temperature, and also Wiedemann-Franz law, and all these things were explained by Drude theory. Now let us let us find what are the basic points of this Drude theory. According to this theory, atom inside a metal is considered as composed of two main parts. One part where all the electrons are filled in the shells plus the nucleus, and second part those electrons which are in the outermost shell of the atom of metal. These electrons which are in the outermost shell, they are considered as conduction electrons, conduction electrons, and inner part which is filled, you can say, and positive in nature, that is considered as core, and electrons in this portion are core electrons which are not participating in the conduction of metals. Further, these conduction electrons which are in the outermost orbit or shell of the atom are considered as free electrons in this theory, and these electrons are just like the molecules of kinetic molecular theory, which means these electrons are always in random motion in analogy with the molecules of kinetic molecular theory. Here, these electrons are always in random motion in all possible directions in the metal. We can assume a piece of metal in which these cores are embedded as per the crystalline structure of the metals, and these all are heavy positive parts of atom, and the remaining outermost electrons which are considered here free electrons, they are shown as free particles or free electrons in the body of this piece of metal, and these electrons can move randomly in all the directions like molecules in the molecular theory are considered moving in all random directions. Here, these free electrons are assumed that they are moving in all possible directions in straight line. So, all these electrons are moving in this way randomly. But this random motion of the electrons in the metal do not constitute any current. Therefore, we say that when there is no voltage applied across the metal, or when there is no electric field applied across the metal, then there is no current in the metal. It means the random motion in all directions of electrons is not responsible for the current in the metal. Now let us assume this piece of metal is applied under the electric field such that one end of metal is connected to positive terminal of battery and other end is connected to negative terminal of battery, and an electric field is applied across the metal piece, and under this condition each electron inside the metal which is moving randomly in all possible directions, acquire a force, or you can say electric force, which is given by the magnitude of this applied electric field. And due to this force of electric field, these electrons are these electrons are forced to move against this electric field. That means the motion of these electrons due to this force will be opposite to the electric field. But the motion of the electrons cannot be in straight line because of these positive charges embedded in the body of matter. And therefore, when electron tends to move against the electric field, the each electron collide with the cores which come under its way, and this electron collide with one core firstly, and then it collide with the another core during the motion, or during the acceleration it acquires due to this force. And we consider that in each collision between two cores, the electron starts with initial speed 0 and it acquires a speed v in a time t. And this way, each electron keeps on colliding with different cores, and then it reaches on the end of this metal. It means it is not coming straight, but it is coming colliding with the cores. So this is not a straight line velocity. This is a kind of drift towards this side and colliding with the other cores. And the velocity which it acquires towards x-axis, negative x-axis, that is termed as drift velocity. And it is denoted by Vd. Now this velocity is totally different than the velocity electrons acquire before the application of this electric field. And this velocity during random motion may be denoted by this v. And this velocity is totally due to the thermal motion. And this thermal motion depends upon temperature. And the velocity of thermal motion during thermal motion may be given by kinetic energy of these electrons half mv square, which will be equal to 3 by 2 kT. That is according to the kinetic theory of molecules. And in the same way, we can find the velocity of these electrons when there is no electric field. So it is very clear that this velocity is only due to the thermal motion of the electrons. But when electric field is applied, then these electrons come under the effect of this force, and then thermal effect starts reducing and effect of this force starts increasing. Now, due to this force, if one electron collides with one core, and then it will moving this side, and then it will collide with another core, naturally it is not going along x-axis, but it is going oblique to the x-axis. But in this course, it will certainly cover some distance along x-axis. in this direction. And let us assume this distance is x between when it moves from one core to another core. And this distance each electron is moving when uh, the electron is moving between any two cores. So every electron will cover some distance along x-axis, which will be under the effect of this force generated by the applied electric field. So in this context, we can find how much acceleration this electron will acquire under the effect of this force, and that acceleration may be written in the form as force. We can write m into acceleration, that is m into, you can say, double derivative of displacement, and it is equal to minus e times e. This is because the force under which electron will move, it is opposite to the electric field, and this acceleration we can determine d2x by dt square, that is acceleration, and it is given by minus e divided by this m times applied electric field. This is the acceleration, and from this acceleration we can find how much velocity this velocity is acquired by this applied electric field. And this velocity we can find, this velocity can be given by acceleration times t, which means we can find the acceleration is d2x over dt square times dt, and we can find from 0 to t. Here this is t time from in which the electron moves from here to here. So from 0 to t times, how much distance is covered by this electron along x-axis, that can be determined, and how much velocity it acquires during this motion up in the end or in the t time, that can also be determined from here, and we can find it as, we know d2x by dt square, from here it is minus e, so minus e times electric field divided by m, and multiply by integration of dt from 0 to t, so it will give you t, therefore minus electric charge multiply by electric field into t divided by m. So this is the velocity, acquired by electron between two successive collisions. We can write minus e times t over m. Now from this velocity we can find how much distance x is covered in this t time, and that is determined by using this formula, that velocity is distance over time, which gives me distance traveled will be equal to velocity time multiplied by time, and from here I have to find the distance covered from one collision to another collision in time t, and we can find x is equal to, let us say, v times dt from 0 to t, and here v is, we know it is this expression, so we can write minus e, capital E over m times t into this dt, and let us integrate from 0 to t. It gives me minus e over m into t square into t square and 2m. So this is the expression of x. Let us write it as x is equal to minus e capital E t square divided by 2m. Let us mark it as equation number 1. So this is the distance acquired by the electron when it moves under the effect of this electric field, and between two collisions, between this, it collides firstly this, and then its velocity becomes 0. Then again it starts under this acceleration and it acquires this velocity in time t, and during this it covers some distance along negative x-axis, and that distance is given by this expression. Now as we know that before applying this electric field, all the free electrons were moving under the thermal effect, and that means motion was thermal motion, which can be determined by this relation, and all these electrons are in random motion and do not constitute any current. So if there are n naught number of electrons in this group, then we can find how many electrons acquire the drift velocity, or we can say this velocity along the x-axis, negative x-axis, under the effect of electric field. And this relationship may be given by Poisson distribution, which is n is equal to n naught e minus t divided by tau, where n naught is the number of electrons in a group which are moving under thermal motion, under thermal effect here due to temperature only. And we know from this relation that when in the starting, if t was 0 in the starting, then from this expression this t0 means it is making 1, e0 is 1. So all the particles and not particles in the group were moving under the thermal effect. But after long time, that means when time approaches to infinity, then this infinity will make e minus infinity will be 0. So therefore n will be 0. It means after long time, all the particles will come under the effect of this electric field, and they will move, they will drift towards left hand side or towards minus x-axis, and no electron will be there which is moving under the effect of thermal conditions. And the change from this 0 to infinity, this n naught to 0, it can be shown by the change in number of particles moving under thermal conditions, and that is given by dn over dt, and it can be determined by differentiating this term, and we get n naught e minus t divided by tau, and divided by this tau differential coefficient with this minus sign. So this is the number of particles, number of electrons which are changing from thermal to the motion under this applied electric field. Now if dn number of electrons in dt time moves under the effect of applied electric field, it means they will also cover some distance along minus x-axis, and total distance covered by this dn electrons along x-axis in dt time can be determined by taking integration of this number. That means that distance may be denoted by x, and it is given by the distance traveled by one electron multiplied by total number of electrons which are now moving under the effect of electric field, and integrating from 0, because initially no electron was moving under the effect of electric field, then up to infinity means when all the electrons will be moving under the effect of electric field. And this equation will be written as 0 to infinity x times, let us divide dn by dt and multiply by dt. Now this is the change of electrons which are moving with now under the effect of electric field, but earlier they were moving under the thermal conditions. And when we change this limit, then the limits will also change, because initially when there was no electron moving under the effect of electric field, then the infinite time was there for its conversion. But when all the electrons are now moving under so there is no time for change. So we put it here from infinity to 0. And if it is so, let us substitute the value of x and substitute the value of dn by dt. We will take value of x from here. So we will write integration from infinity to 0. Value of x comes from here, that is minus E times electric field time square divided by this 2m times, now value of dn comes from here, that is minus n naught E minus t divided by tau times dt. And on rearrangement we get this. Here one thing is left, that we have to divide this by n naught also, because I have to take the average. So we will find total distance covered by d in n electrons if one electron covers this much distance. So this will be the total distance covered by dn electrons divided by total number of electrons. So here we will also write n naught. We will write n naught here also, and this n naught will cancel out with this n naught, and we get this average distance traveled will be equal to, we take E and this E common, minus minus will become plus, so we get E times electric field divided by this 2m and this tau, 2m times tau, and inside the integration infinity to 0, what we get is only t square times exponential of minus t divided by tau to dt. Now its solution can be written from the standard result, and that is equal to minus 2t cube. Therefore result comes out to be E over 2m tau times minus 2 tau cube, where this tau is relaxation time. We have introduced this tau here, and this tau is called relaxation time. and relaxation time is the average time between two collisions. So here 2 cancels, so 1 tau cancels, we left with 2 here, so we get minus E times electric field times tau square divided by m. So average distance traveled by all electrons is given by E times tau divided by m. Let us mark this equation as equation number 2. Now let us assume the metal which we are considering that has dimensions like, suppose it has area A and it has length L, area A, and if I current is established, if I current is there inside, then naturally we know that current is written as total charge divided by time, and total charge means charge on one electron multiplied by total number of electrons divided by T. Now total number of electrons in this sample, that means free electrons, can be determined by knowing that how many, that number of electrons per unit volume, that means number of total electrons divided by volume of the metal, and volume is written as area times length of the, so it means we can find total number of particles per unit volume in any metal, and therefore if n small n is known, then total number of particles in this, total number of free electrons in this metal base we can find, and that will be equal to n times A times L. And if it is the value of n, let us substitute here, we get E times NaL divided by this time T. But we know that length over this time, that means total length of the metal surface, and the time in which it covers with the drift velocity, that gives you drift velocity. Therefore, we can write E, N, A, and Vd. So the Vd means here we have L over T. So it means current may be written as N times E L, not L, A times Vd. But if I take A to other side, or you can find from here what is Vd. So drift velocity from here I will get current divided by these values, that is N E times A. Now this is, let us say, equation number 3. Now if we see in equation number here, equation number we can find x here, and from here we find what is average distance traveled, that is this. So using equation 2 we can find the expression for drift velocity as velocity Vd is equal to average distance traveled divided by time for average time, that is tau, or relaxation time, and we know that average time is given by this, that is minus E, capital E times tau square divided by tau, and it gives me that Vd, drift velocity, is equal to E times tau. E times tau over m. Here we will get m also from this expression. So this is drift velocity. Let us say this is equation number 4. I have omitted this negative sign because this negative sign is simply telling me that drift velocity is opposite to the direction of electric field. So it is not contributing in the magnitude. Therefore, magnitude of drift velocity is this. Let us compare 3 and 4. We are comparing equation 3 and 4. So on comparing equations 3 and 4, what we find is that I divided by, from here, NEA is equal to E, capital E, electric field, tau divided by M. But here current per unit area is called current density. Therefore, we can write J, current over area, that gives me J equal to, I take N into E to the right hand side, I get N times E multiplied by this E, I get N E square tau divided by M multiplied with this electric field E. And from here, this equation may be written as J times J equal to, let me put here sigma times E, where sigma is equal to N E square tau divided by M, and this is called conductivity of metal. It means the conductivity depends on these microscopic properties, that is how many number of particles per unit volume in the metal body, then charge of the electron, then what is relaxation time between any two successive collisions, and mass of the electron. And this equation J is equal to sigma E. This is known as Ohm's law, or you can say microscopic form of Ohm's law. So it shows that Drude theory of metals can be used to explain or to derive Ohm's law in its microscopic form, and expression for that is J is equal to, that is current density will be equal to conductivity times applied electric field across the metal piece. Now we know that electrons are colliding with the cores under the effect of electric field, and this collision between the two cores, during this electron covers some distance, and the distance covered between any two collisions is different for different collisions. But if we find on an average the distance between any two collisions, that average distance may be taken as mean free path, and that is denoted by lambda. Lambda is here mean free path. That means it is the average distance which electron travels between any two successive collisions when moving under the effect of thermal conditions. That means before applying the electric field, when electron is moving, even then it is colliding with the particles or cores, then average distance traveled at that time in the absence of electric field, that it is called mean free path. And this mean free path is related to the relaxation time, and that is given by tau is equal to mean free path divided by thermal velocity, that we can show as thermal velocity. But as I explained, that thermal velocity can be determined by using formula of kinetic energy, that is half m v square is equal to 3 by 2 kT, where k is Boltzmann constant. Then from here, if you find v, we get v will come out to be, this 2 cancels and m comes this side, therefore we get 3 kT divided by m square root. Let us put this value v here, which is thermal, this is thermal velocity. Let us put this value here, so we get tau is equal to lambda times this thermal velocity, that is 3k T over m square root, and it gives me lambda times m over 3k T square root. So this is the expression for it. And if we substitute this tau, this time, relaxation time, in this expression sigma, then sigma conductivity will become, because I have to put tau here, so I will get Ne square divided by m multiplied by this tau, which is given by this expression, that is lambda times m over 3 kT square root. Which gives me E square n lambda divided by 3m kT square root. So in this expression you find the numerator everything is constant, in denominator 3mk is constant, but T is varying here, conditions are varying with temperature. So therefore we can say that sigma, or we can say conductivity of the metal, is inversely proportional to temperature square root of the temperature. So this is another finding of the Drude theory, in which it is explained that electric conductivity of the metal is inversely proportional to square root of the temperature. Now let us mark this equation as equation number 5 for its use later on. We can equation number 5. Now let us assume a metal surface, or a metal of certain dimensions, such that it has area A, and let these two areas of the surface of the metal are separated by a certain distance x, area A. Let us assume that one end of it maintained at temperature 1, other end is maintained as temperature 2, such that these two ends have fixed temperatures. Therefore the temperature will change from A one end to the another end, and if it is x distance away, then we can say there is a temperature gradient along the length of the metal conductor. And under these conditions, we can say the transfer of heat rate of transfer of heat from one end to the other end will be measured by using one equation that is given by dq, that is heat changing with time, equal to minus k times area of the metal body times gradient of temperature. So this is the equation which can be used. Now this temperature is the measure of heat exchanged between two ends, and according to transport phenomena, for transport of heat energy, the amount of heat passing through a cross section of strip like this per unit area and per second, that is given by another equation which we can write as dq over dt is equal to 1 over 3 times number of electrons per unit volume in this, multiply with thermal velocity it gains, with mean free path and the change in energy with distance, that is energy gradient. So this is the relationship. Here dE over dx is called energy gradient, but we have learned that this thermal energy V thermal is given by 3 kT over m square root, that we have determined here. So this energy is given by, and what is this E? E is 3 by 2 kT, that is kinetic energy of the electrons. Now if we differentiate this equation, then we will get dE divided by dx is equal to 3 by 2 k times dt over dx. That means it gives me temperature gradient, it gives me the energy gradient. In this equation we have energy gradient, in this equation we have temperature gradient. Now let us substitute the value of this dE over dx, that is energy gradient, in this equation here, and we also substitute the value of thermal velocity here. Then this equation, that is rate of transfer of heat, this rate of transfer of heat may be given by dq over dt equal to this 1 over 3, we will get 1 over 3 times number of electrons per unit volume times the value of thermal kinetic energy, that is thermal velocity 3 kT divided by m. This value I have substituted here, times lambda, that is here, into this energy gradient which we can mention from here, that is 3 by 2 k times dt over dx. So on solving this equation, we can find what is the dependence of temperature. This temperature is here, which is under square root. So therefore I can write this equation as transfer of heat due to thermal conductivity, rate of transfer of heat is given by half because this 3 will cancel out, this 3 will cancel, so we left with only half. Number of electrons per unit volume multiply by this mean free path lambda times 3k, which we left here 3 by 2, because we have k here, we have k here, so 3 by 2. Similarly, you can put this 3 here, so 3 by 2 times T square root into temperature gradient. So ultimately we found that the heat transfer rate of heat transfer is directly proportional to this square root of temperature. Now let us compare this equation of dq by dt, this transfer of heat, with this equation which we have written here. Then we find on left hand side we have dq by dt here, and we also have dq by dt here, and on right hand side we have dt by dx here and dt by dx here. So it means the remaining portion minus ka will be equal to this portion, and it implies that minus, let me change color, it gives me minus ka is equal to this remaining portion, half of n number of electrons per unit volume times mean free path times 3k power 3 by 2 time temperature square root. And from here we can find that k is equal to, that is coefficient of conduction, that is given by 3 times k, that is Boltzmann constant, and this is conduction constant, 3 times k 3 by 2 number of electrons time this mean free path divided by 2 times area into temperature square root. And it shows that thermal conductivity is directly proportional to, it shows thermal conductivity is directly proportional to square root of temperature. So this is one equation where we found that thermal conductivity is directly proportional to square root of temperature, and in this equation we found here that electrical conductivity is inversely proportional to square root of the temperature. So these two values are totally different. Means now if we take the ratio of this thermal conductivity, that is K and K to the electrical conductivity sigma, then we found that it is this one. This one is directly proportional to root T, and this is inversely proportional to 1 over root T, or inversely proportional to root T that comes in the numerator, and it gives me T, which is constant temperature. So it means that thermal ratio of thermal conductivity to the electrical conductivity is constant value. And this law, that is ratio of the two, that is known as Wade's Weidman, or we can say Weidman-Friend's law. So this is another law which is explained by using Drude theory of metals. So let us see what we have learned by using Drude theory. By using Drude theory, we are able to explain the microscopic form of Ohm's law. We have explained that electrical conductivity is inversely proportional to the square root of temperature. This, this theory helps us to explain that thermal conductivity is directly proportional to the square root of temperature. And finally, it has successfully verified Weidman-Friend's law. So that's all about the Drude theory. Thank you for watching this lecture.